Okay. Welcome everyone to this parallel breakout session. Today we have John David who will be conducting this tutorial. I'll be acting as a moderator and assisting to pass questions and discussion. Please participate in this discussion so it benefits all to learn efficiently. And you can raise your hands or put questions in chat box. Only keep muted when you are not talking, so we avoid any echoes or noise. So John is a software engineer on joined NASA NOAA GOES-R Pro Pass team at NASA JSFC, and he keeps visiting NOAA and other sites also for his work. He has worked on various hydrological modeling and remote sensing projects. He has professional experience in art, robotics, artificial intelligence, and most recently, restoration and conservation ecology. So today he will be sharing his knowledge on machine learning and artificial intelligence and how to get started with it. So I hand over to John, please.
Thank you very much. I thought I should also mention that this session is being recorded, and that was pre-decided by the symposium. So if you don't want to be recorded, just please be aware that it is being recorded. So the title of my presentation today is Machine Learning and Artificial Intelligence. What are they and what do I do to get started? Oh, well, I got it clicked off. So anyway, a little bit of bookkeeping. There's been an issue with downloading this to a public accessible drive or FTP site. So the intent is to actually have the presentation available to everyone through the Python notebook. But part of my experience is that when I run these things, quite often, if something happens and it crashes in the middle, if you have to go all the way back to the beginning to load stuff, it gets a little nuts. So the very first thing that I have here is loading up all of the packages, for the presentation. However, when you download the notebook itself and as you're running it independently, I do try to make a practice of re-importing all of the packages so that you can start at any of the section boundaries. If we go to machine learning and artificial intelligence, the first question is kind of what are they? And what's the differences, kind of what's the boundaries and the limits? Well, machine learning was first coined by Arthur Samuel in the study of computer algorithms, architectures, and statistic methods that learn things from observed facts. This is widely seen as a subdiscipline to artificial intelligence, and they are used widely. Machine learning is used widely in a variety of applications, such as medicine, email filtering, computer vision, all sorts of stuff, where it is difficult or unfeasible to develop conventional algorithms to perform the needs for the task. Artificial intelligence was first coined in 1956 by John McCarthy to distinguish itself from the field of cybernetics. And he was focusing on systems that think or act like humans. Later on, people realized that this was rather limiting, that there are other systems which act and think rationally, but have no connections to how we understand humans thinking or acting. And so it was broadened out later. Now, one of the things with all of this is that there's a lot of debates about what constitutes an actual machine learning or artificial intelligence system. And I mean, it's almost gotten to the point where there's almost like a holy war about, where the limits are. And but no one disagrees that systems like Watson, and I'm sorry I didn't get the citations for all of this cleaned up, RAI systems, or the recent developments for prosthetics, where there's a new smart prosthetic which actually can sense the electrical signals in the nerve endings of the muscles of an amputated arm, and actually act as a smart prosthetic. And no one's going to disagree that that's a machine learning, a successful machine learning program. But on the opposite extreme, you've got very simple things like linear regression, principal component analysis, and general linear models, which actually many people consider actually part of machine learning, and in some cases part of artificial intelligence. But regardless of what is and is not considered machine learning or AI, or how simple or complex they are, all of these different applications have one thing in common, that they all require data, and they all require very often a massive amount of data. And I've worked on systems where we've had thousands or tens of thousands of images in the training data sets. So we can talk about like massive data sets. Sometimes these are petabytes in size. And so the question is, how do you go about getting started with any project? One thing that a lot of people gloss over is basically just dealing with getting in the data using things like Pandas, xray, Dask, and then there's some new tools available, such as Intake. And so I'm going to go over some very, cursory examples about some of the techniques that are used there, some examples. The initial sections are really intended to be a working notebook, so that you can go back and see, like, okay, how did I read in a CSV file in Pandas? How did I open up a, say,
John, you are muted.
Have I been muted this whole time?
No, it was my fault. I am so sorry. Continue on.
Oh, okay. Where did I get muted? What was the last thing people heard?
Just few seconds, I think, back. So.
Okay. So moving forward with starting with Pandas. I'm going to be borrowing very heavily from a lot of other people's work, and I have tried where possible to give the original links. And so as you get a hold of a copy of this presentation, you should be able to follow these links to see the projects. I've got a section for references at the ends, etc. So there's a lot of information that you can follow up on. And so Pandas, well, what is Pandas? What is it intended to do? Well, it really was set up to basically be a front end for comma-separated files and basically one-dimensional data that's coming in, similar to your Excel spreadsheets. This, of course, has grown later on to include many different formats. But part of the intention here was to work with very large data sets and both Pandas, xray, and Dask was set up so that they can actually ingest very large data sets. I've seen Pandas actually read data sets that have like over 1 billion elements. I myself have used xray and Dask to actually process 2.5 gigapixel images that were so large they actually wouldn't even fit into the physical memory of my machine. And so some of the techniques that I'm going to be showing you is how these things are worked out of core, which means that the algorithms are set up so that they operate on little chunks of the data, and that later on they are processed and then stitched back together so that even on a very small machine, like let's say your laptop, you can actually fully process gigapixel images. You can fully access all of the cores on your machine and other resources to actually process all of this. Well, some of the intents and key features of Pandas is fast and efficient data frame objects with default and customized indexing. There's tools for loading data into memory objects from different formats. The data is intelligent and actually has metadata attached to it, so that it helps integrated data handling and missing data. You can reshape and pivot data sets. You can actually label-based slicing, including date and time. The columns from data structures can be deleted or inserted. Groups of data can be aggregated and transformed. And Pandas, which was originally designed by the financial industry, is actually intended to be super, super fast. And so this is very, very efficient. And here's some of the overall features of Pandas, including masking data, merging and joining data sets, etc. And so if I go ahead and, here's some just examples. So here I go ahead and I read in a time series for sea ice. As a note, as much as possible, I'm actually utilizing NASA and NOAA data for Earth systems data. And in my examples, it's not entirely the case, but I do actually use them when possible. So here with just Pandas, I go ahead and actually read a standard time series sea ice data set from NOAA. And if I go ahead and I look at the data frame, I look at the information about it, it tells me that I have 255 entries. I can see that I have a column that deals with the time date stamp. I have a column for measurements in the Arctic and a column for measurements in the Antarctic. And I also printed the head. And so the data frame, you can say, just tell me the first 5, or if you do tail, just the last 5 objects, so that I can just give a quick view of my data to say, does it look reasonable and sane? One of the things that I'm doing throughout here is very often I will very quickly visualize something, whether it's just a little text dump or an actual image, and just so that I can continually check as I'm developing the code to see, is it processing what it looks like correctly. Now, one of the cool things that's built into Pandas and xray and several other tools is something where I can describe the data set. And this is basically a statistical summary that tells me how many objects there are. It actually tells me the statistical mean, the standard deviation, the minimum, the maximum, and then the 25, 50, and 75th quantile. So if I look at Pandas and the data structures, they are very similar to NumPy ND arrays, but with extra functionality. In the 1D data structure is actually called a series, and it is a labeled array capable of holding any data type or collection of data types, including integers, strings, floating point numbers, Python objects. They can be anything arbitrary. The access labels are collectively referred to as the index. And you can think of a series as a cross between a list and a dictionary. And so here you see an example where you have an index. In this case, it's an ASCII alphanumeric, and it actually indexes the array or list of floating point numbers. And so just to give some very quick examples, I will set up, I actually created a Pandas series by first creating a simple list, and then I'm going to create a NumPy array from that list. And you can see here that they are in fact the same. And then creating a series is nothing more than passing in that NumPy array into the Pandas series creation routine. And so here I actually print out the type, and so you see the type of SR is the Pandas series series. And if I print SR, I actually see the exact same data as I had before, but now it's in columnar form. And so I can get anytime that I have a series, I can print out its values, I can print out the index, I can give a list of my rows and my index values, and I can also describe it. So now this description, if I go back up here, no, that was a different description. The above was the Arctic sea ice. Now I've got something that I've just thrown together. So my descriptor isn't, I don't have something to actually show that it's the same as before. But the NumPy array has an implicitly defined integer index, which we can use to access the values, while the Pandas series has an explicit defined index associated with the values. And so I can get the value from the nth position in the series. I can also use iloc to get the value at position n, and also access the value giving a dictionary-like syntax using log. Now, the way I set this up, I was going to go back and try to do something that was a little more in depth here to show what the differences were. I didn't have time to go back and add that. There are actually differences here, but just knowing that you can access the values from your series in several different ways. As you go and you play with them and you run into a problem where all of a sudden, how do I access that? You can go back and you can try a couple of these different ways and read up on them. Well,
John, there is a
yep.
question from Mahi.
Sure.
Was that an array or a list which was passed into Pandas series?
I think that was an array, but let me see. Yeah, so if I look at this series, yeah, here it is. It was a NumPy array, ND array.
Okay. I hope that answers.
Okay. Okay, so now so much of what we do is actually two-dimensional labeled data, and so here you have a data frame that is like a sequence of aligned series objects, and they can actually share the same index. And what's nice is later on, and I can't remember, I don't think I actually included this here, is that you can have multiple series and then you can actually merge them in. And as long as the indexes are the same or the same type, that you can now basically concatenate or merge different data sets so that, in essence, you can add new columns or you can append stuff at the end, etc. And so it ends up being an extremely robust and powerful tool. And so here's an example of actually creating in Python a data frame directly, where in essence I have the let me see, the index, but in this case I'm defining the index via characters as opposed to numbers, and I have the columns as basically a number, a bool, a string, a real, to give examples. And if you also notice in the real numbers that I'm actually putting in one that is not a number, it's not defined. And this is very useful, and dealing with missing data is one of those things that can really trip you up. And I actually have a couple of simple examples going forward in how you deal with this and how you change it. So once I've created this, I've actually, so the type is, now I have a Pandas core frame data frame. And if I dump the info on that, you'll notice that not only does it tell me that it's a data frame, but it tells me that I've got 5 entries and my indexes range from A to E, and that I have the column name and the type, the data type. And so again, using info gives me a lot of information. I noticed something twitching on the side. Was there more questions? I guess not. I guess Ankush posted the notebook. Great.
Yeah, so I posted a notebook so people can download and view it.
Okay, thanks. Okay, so here I go ahead and I describe it again, which is this basically this statistical summary. And what's nice is you remember that I had a nan, or undefined entry there. And describe is actually smart enough, and many of the statistics are actually smart enough to ignore missing data and still calculate properly the means and statistical deviations and stuff like that. And so this is a really nice way to just get a sense that everything is looking good. As I said, here's how you access the actual column names, and you can actually get a specific column by accessing it with the df column name. Now, this one is interesting because you'll notice that there's I'm actually passing in a list of strings, and the strings are actually the column names. And so by passing in the list of column names, I actually am creating a new data set that has just those two columns of, I think the original was 3 or 4. And if you'll also notice that I swap the order, where before it was set up num bool string real. And so here it's num followed by real, and I can actually simply reorder them this way. And there are other ways to reorder them as well. But this is just a cool little trick. And so I'm sure that a lot of you have dealt with masking data. Pandas is actually works exactly the same as you would expect or you've experienced in NumPy, that you can actually have it subset the data using various masking techniques. And you'll notice as I do this, excuse me, in this particular case, it actually dropped the missing data. And so this is, part of the whole thing with problems with NANs, and that the NANs don't compare to equal. And so there's different comparisons that you need to do in order to do these to actually compare. In specifically, Pandas and NumPy uses the fact that NP-NaN does not equal NP-NaN and treats none like NP-NaN. And that's very advantageous, but it ends up tripping you up if you've got missing data to actually figure out how to deal with the NANs. And so just to show it off, I've got yet another way of accessing the data. And you'll notice that there's a NaN in the middle, but if I, to verify that the equals operator doesn't work, then I say, I compare all of this and I see that C is false, but if I look above, it's actually NaN. But if I go ahead and use is null, and over the entire data set, well, you'll notice that there's no missing data anywhere else except in the real in C. So you can see this being true here. Now, if you want to see is there any missing data anywhere at all, then I can say is null. I can look at the values and I can say any. So if any of them are true, then just return true. I can also say how many of them are in each one of the categories. So I see that there's one in the reals column and there's none anywhere else. That's just some basic, using Pandas, but for doing a lot of things that we do at NOAA and NASA, we have, huge time series data sets. So, now let's go ahead and just play around a bit with date time and date ranges. And so here I'm actually creating a date range. I've got a start date, and then I tell it I want 15 periods and I want it to go hourly. Now, if I go ahead and you see I'm often just typing out I'm printing out the type just so that to help you see this. Normally I wouldn't do this, but it's just sometimes useful to see it. And then I go ahead and I print out DTI. And what I see is there's 15 of them, and you'll notice that starting at hour 0, going up to hour 14, so 0 to 14 inclusive. Now, one of the things you notice that this doesn't have any zone information, but I can go ahead and actually modify it in place just by setting the zone. And you can actually, once you have the zone set up, you can actually transfer from one zone to another, or if you have a zone a data set that is in some local time, you can actually translate it back to UTC. And so this is, very easy to basically localize the data sets. And so I'm going to go back and I'm going to create a series of data, and the length is however many data series objects I have, which is 15, and then I'm going to go ahead and set the index to 15. And so this is actually going to create the series so that it's indexed by date and time. And I'll go ahead and print that out so you can see it. The nice thing is, on the fly, I can actually completely resample my data set. So I'm looking at, let's say I want to resample for every 2 hours, and I want to give the mean for, in this case, it would be, the 2 hourly entries, give it the 2-hour mean. But you can see how simple it is to actually resample your data and generate some very, very simple statistics. Now, xrays are actually set up, they're intended to be an efficient way for dealing with raster data, in particular, or two-dimensional gridded data, in particular image data. And so the example I'm going to show you here is I'm going to walk through manipulating a netcdf file that I downloaded from NOAA's NCEP Reanalysis. As a note, the Reanalysis project uses analysis and forecast system to perform the data assimilation using the past data from 48 years to present. And so kind of a side note to this is to be aware that there are data sets out there that go back, well, this one is what, 73 years. And so there are available some data sets that are very, very useful to help you as you go back and analyze things. And so the one particular one that I downloaded, which I think was the air, and I think this was air at 2 meter, if I recall correctly. And so I have the air temperature that's 4 times per day for the entire year, which turns out to be 1,460 records. So using the xray open data set, I can actually, as long as I have access to public access somewhere, I can actually just access it via its URL, which I find very useful. And so here's an example where I go ahead and grab the air temperature from 2018. And then for the data set, I'm going to look at the keys. And so this is basically produces, or it dumps the, in this case, netcdf metadata that's attached to that document to give you pretty much the same information as you would get from netcdf dump with, I think, a -h option. And you can see that I've got lat long, I've got time, I've got the air temperature, I've got some, metadata in here about, it's 4 times daily. It was created at the end of 2017, which doesn't make a lot of sense since it's a 2018 data set. I think that might be an error. And then it actually has a URL reference for the data. I can also basically get and manipulate these attributes directly. And so here's how I've accessed it as a Python dictionary. And from here, I can actually, if I wanted to do something with, let's say, the metadata reference, I can actually, here's yet another form that I can access it. So an X-ray contains, as I said, the metadata, making it self-describing, and it can pass this along as you are actually processing it. And so here in this case, I'm going to go ahead and take a look at the air data set, and I see that I have, wait a second, have I? No, I haven't gone in yet. So I've got 73 latitudinal bands, 144 longitudinal bands. I think they were like, what was it, 2 degree or something like that. And so you can look at the type, et cetera, et cetera. And so now if I wanted to get the lat long values, these are actually, the positions, basically parts of the grid. And I can also access the attributes here, for it. Again, these are, I'm doing things in several different ways, in part to help you, to give you a resource to go back and look and to get ideas of how things, how you might do things. So here I'm able to actually get a hold of the minimum and maximum values for the latitude and longitude. And then I'm actually looking at some of the time. So what's the minimum and maximum time dates for it? And as you can see, it starts from the beginning of the year to the end. And I also wanted to look at, since X-rays just went off and created this thing kind of on its own, how did it, what is the actual type? And so if I look at the type, I actually see that it returns a NumPy ND array. And the shape is actually a 100, it's basically a one-dimensional array. So here I can actually slice the data and select XY combinations. And so here what I'm going to do is I'm going to give a lat long for position, and Lenham, Maryland is, this latitude longitude position is about 1 mile south of NASA Goddard, and it's very close to my home and my farm. And so I went ahead and set it up there. And I will also note that here I had to add 360 to it because the longitude, as I found it, was plus or minus 180 instead of 0 to 360. And so as you're going along, you might have to massage the data a bit to actually get it to work for you. And if I didn't do that, as I move forward, it would actually crash. And so, I plot it back out. There's the longitude and, 0 to 360, latitude, etc. And so now I want to just visualize it. Where is the latitude and longitude of my slice? And remember, this is basically a single point. And so I will go ahead and use matplotlib to actually generate a little map with a little star to say, where am I? And then I am going to subset the data set by interpreting it at that single. And so there are several different access methods for interpolation and extrapolation, and I didn't have time to really go into these details, but just know that when you are giving ranges and things, you actually sometimes have to find the actual lat-long boundary, which I showed you above how to get a hold of, and so that you can then go and extract portions of your data set. But in this particular case, I'm using interpolation. And when I look at the array, I forget, I don't think I printed how, yeah, there's still 1,460 points where it's the same as it was before, except before it was the full two-dimensional data set. Here it is a single point, a single location, instead of that many global covered 2D arrays. And so here I want to do a really quick, and both Pandas and xray actually has some very simple plotting and display capabilities. And so here I'm going, and one is actually a, as you see above here, it's actually a xray data array. And I'm going to just plot it using a line. And so you see this here, a very simple plot, and it got the latitude and longitude from the metadata. It also got the name over here from the metadata, and it got the date range. And so as long as you use fairly standard indexing, etc., you can actually generate very nice graphics. But that said, matplotlib actually does a much better job and is much closer to being publication ready. And so I basically do the same thing again here. I've added a few things with, making dots instead of lines, etc., and, using matplotlib. To show a different way that people like a lot better. It's actually much more feature rich. There's many things you can do with this plot where the plotting or display capability that xray and Pandas gives you in itself is very, very limited and really intended just to give you a quick way to visualize a data set. So now that I've already sliced the data set by location, I now want to go ahead and do it again by time. And here I can just simply use the selection operator, and I say time, I slice by start date and end date, which I set up here. And then I go ahead and I interpret that with the latitude and longitude. But if you remember the air temp 2D, that's the entire data set. That was not the data set that I had gone ahead up here and had subsetted the one point. I basically completely reran the subset in that one line. And so there's a lot of these operators that, you're probably accustomed to doing this in NumPy as well, that you can go ahead and pass along in the execution chain. And so in this one line, I basically subsetted not only space, but also time. And I'll go ahead and use the nice matplotlib to actually show the time series and generate a little example. But I can also generate, let's say, along a single longitude, I can have several latitudes. And you might think, why do I want to do that? Well, my wife is a research ecologist, and she has a long-term data set where she has plots at 5 different latitudinal bands, and she uses latitude as a surrogate for temperature and climate change. And so, part of what I wanted to show you here is that just like passing in arrays of indexes in the data frame above in Pandas, I can do the exact same thing in xray. And so here I've got 3 different latitudinal bands in a single longitude, and then I'm plotting them against time. And so it also shows you, Okay, so we can also slice the data across spatial extent for a specific record in time. And so, much the same way with the RTD as well. And then I can just kind of plot it to see, roughly where this sets as well. So now I want to get into a little bit more with spatial plots, but specifically dealing more with imagery. And so here I'm going to do, so I subsetted a 1 day of data, and I'm going to go ahead and plot it, and I'll set the XY axes, and also I'm going to be selecting against time, and then I'll go ahead and plot the subtitle here. And so as you can see, I've got latitude in degrees north and south, and then I've got different times for the single day. So before, when I subsetted for a single day, remember that these images are produced 4 per day. And so just this one command was able to subset the data and then do all 4 of the plots to give you an idea of what's changing in that day. So let me see, it's 10 minutes till, okay, it's 10 minutes to the hour. And so, or well, 13 minutes to the hour. So this is going to be a really good place. I think I'm going to take a break so everyone can get some tea or hit the facilities. And let's plan to be back in 12 minutes. Does this work for everybody?
Yeah, I think that is a good idea.
Okay. And when we get back, I'll start back up with Basque.
Okay, so let's start at means after 15 minutes, right? That's enough.
Yeah, my intention is to start at the top of the hour. But yeah, 10 minutes, 12 minutes,
Yeah,
yep.
10, 12 minutes. Okay. And if anybody has questions, please post in the chat box from whatever John explained. If those can be clarified as soon as we start.
Oh, has anybody been able to download the Python notebook? Good. Just wanted to check so that we had a few minutes to do stuff. Yeah, if there's any questions, I'll stick around for a little bit.
I think people have downloaded it and maybe they will put questions. So John, you can take 10-minute break.
Okay. Yeah, somebody just asked if the recording will be available, and my understanding is yes, but I don't know how that will be distributed.
Yeah, those I think you will get email from Sharon or Kendra. Those will be available.
That's correct.
Yeah.
Okay, I'll take off. I'll mute and take off now. I'm back, everybody. I'm going to give people, 3-4 more minutes before I start again, but I'm here if anyone has any questions.
So maybe in a couple of minutes we'll start, right? So John,
Yep.
what what tips you would like to give who is just beginner for Python, who is there, how they get into learning? They may they are just starting,
I'm sorry,
suppose.
I'm sorry, you broke up a bit.
Can you hear me now?
You broke up a bit.
Hello, can you hear?
Yeah, I can hear. There seems to be about a 3 or 4 second delay, and you're breaking up a little. I'm going to go ahead and skip down to the end for a moment. So part of the resources that I have, useful references, I actually, NASA's Advanced Software Technology Group actually has Python courses that they teach. A whole bunch of the stuff that I've taken from, throughout uh, um, this is actually from there. And I also gave a link to one of Goddard's Python boot camps that they run. Uh, the one from 2016 and I think 2015 or maybe 17, I helped teach a couple of the sections. And so these are intended to basically start from somebody that has a well grounding in like science and or math and very little programming ability at all. And so if you go to STG's Python courses, they actually have some that are for absolute beginners. The Python Bootcamp, now Goddard's Python Bootcamp, there's several of them. I only gave one of them here. They're intended to, like I said, have very little to no programming experience at all and no Python experience. It starts from, pretty much nothing. But it goes at such a good clip that the 3 days that the class is normally taught in, the boot camp is normally taught in, no matter your skill level, it's going to keep you flat out running to keep up if you actually tried to do it in 3 days. And as I said, there's lots of other references here about, basically learning Pandas, like xrays, basic introductions, working with time series, et cetera, et cetera, et cetera. So, I've got lots and lots of background information here for you moving forward. So I think we're 3 minutes after the hour. I'm going to go back up to the desk and start back up with the section on desk. So as mentioned, a lot of the data sets and problems that we're dealing with are just absolutely huge. And so Dask was created to abstract a lot of this stuff with the algorithms so that they work out of core, meaning that it'll work on little pieces in memory and then it'll swap stuff in and out as it needs to, and to provide a very intuitive workflows for also ingesting and analyzing these extremely large data sets, and both distributed and remote data sets as well. It also has native parallel analytic tools, which are designed to integrate seamlessly with NumPy, Pandas, scikit-learn, xrays, just a lot of other things. As I mentioned, it's out of array capabilities, and it's hard to explain how powerful this is. Back before Dask, they made Dask, I actually had to write or rewrite a machine learning, let me see, it was random forest algorithm, and do all of the processing and write it out of core, because we had these huge 2.5 gigapixel images that each image just to load up into memory was like what was it, 16 gig or something. And so now imagine if your algorithm reads in the data set, it does something to it, and then it writes it out. Well, it's got 2 or 3 different copies of it there, and how many laptops do you know that come with something like 64 gig or 128 gig of memory? They don't. And so I ended up writing all of these things, or hacking these things, so that they worked out of core. And once Dask came around and the machine learning community started supporting it, I was able to throw away, many, many thousands of lines of meticulous, mind-bendy code with 100 lines, 200 lines of things that, many hundreds or even thousands of people across the world have helped to develop and maintain. These are extremely powerful tools. So anyway, Dask also provides a few high-level constructs such as bags, data frames, and arrays, Dask arrays, to provide easy-to-use interfaces for parallelizing many of the typical data transformations that you have in machine learning and artificial intelligence workflows. It also allows the creation of highly customizable job execution graphs, and I'm going to show you a couple of these by utilizing their extensive Python API, where you can actually set up the execution in a graph, and you're not executing the actual code, but you're telling Dask how the system is connected together, all the little pieces, so that it knows what chunk of data it's going to get, how it's going to process it, and how it's going to integrate it back together. And so this goes over a little bit of the high-level APIs, the low-level APIs, and also looks at some of the task schedulers. and there's quite a number of them that you can use. Some of the advantages of using Dask is it's fully implemented in Python and natively scales NumPy, Pandas, scikit-learn, xrays, and other tools. And so kind of in its heart, it knows how to deal with these and it makes it easy for them. So Dask is a really, really nice tool when you're dealing with very large data or very large data sets. It can also be used effectively with small and medium data sets on a single machine, as well as across the cloud and supercomputers, etc. As a note, when we were actually working on Dask at NASA way early on in its development, I was able to actually run the exact same code that I was running on the Amazon cloud, develop it on my laptop, actually do timing tests on my laptop, and figured out a very small scaling factor for the actual timing tests on the Amazon cloud, and then be able to actually run 1,000 cores and actually have the timing actually scale predictably from my laptop to the Amazon cloud, running many hundreds or even thousands of cores. So it's it's very, very nice, very useful. So a couple of the things about the Dask arrays is Dask actually coordinates NumPy arrays, and it allows you to chunk big data and then divvy it out and then pull it back together. And again, the out of core or larger than memory lets you work on data sets that are too large to even fit into the memory of your single computer or your laptop or whatever. And most of the stuff that I've worked with is actually blocked algorithms that allows you to basically split your data set into blocks, as you see here, and then very efficiently perform the smaller computations. As I said, they also support a very large subset of the native NumPy API. Not everything, and to be quite frank, I can never remember what's not implemented and why. But as Dask is continuing being developed, they're very regularly adding new and cool stuff. So anyway, to create a Dask array is actually pretty simple. So I've defined a Dask array here. So I imported Dask array as DA. And so just to create a Dask array of random elements, I am telling it I want a 20,000 by 20,000 pixel array, or element array, sorry. And I want to operate on 1,000 by 1,000 chunks. And so that's basically 20 chunks wide by 20 chunks tall. And if I'm not mistaken, that's 400 chunks total. So it's very simple. I just run it through random, and it generates basically random numbers and populates the entire Dask array. So I'm going to go ahead and look at the shape size and the number of chunks, or actually it's not the number of chunks, but I want to take a look at the size, and it tells me the actual size of them. And the reason I'm doing this is that, let's say that I told it that I wanted 1,000 by 1,000 size chunks, but I told it that I wanted 19,050 by 19,050. Well, it's not going to be able to do the entire 1,000 by 1,000 chunk as an example, and so it can actually deal appropriately with odd shaped chunks as long as they're rectilinear blocks. And so if I can also use the NumPy syntax to manipulate the Dask array. And all I've done here is I've taken the Dask array X, and then I've added it to of the Dask array X. And so I'm basically just adding it to itself, but I'm rotating it by 90. And then I can still do some very simple statistics, like I can ask, what's the mean across the axis, etc. And it will go ahead and well, one of the things with this is that it set up the tasks. It hasn't actually executed them yet, which I'll get into in a minute. And so I've looked at, the mean of X, and it tells me I've got all of these different chunks. I've got the array, et cetera. Here's Z, and I'm actually subsetting the data. I'm only looking at the last, 5,000 elements, and I'm skipping by 2. So I'm basically dividing, the chunk, the 20,000 by 20,000 image to 10,000 by 10,000, and the chunks from 1,000 by 1,000 to 500 by 500. And so I'm looking at the details here. And then now if I say I want to visualize it, this is actually giving me a graph of what it's doing. It's going all the way back to X, when X was created as a random sample. And then I'm not sure that I can zoom in. That's not working. Okay, I should have probably done a smaller example here, but each one of these bits here is processing. So here I'm creating the random sample. I think here I'm like subsetting. Then if you remember, I did a this is probably the transpose, and then I'm doing the add, and then I think this is doing the subsetting, and then it's going along. And so you see how all this stuff is going around, and what's cool is that it breaks all that stuff up. It's taking care of how all of the distributed processing is happening in the little chunks so that you don't have to worry about it. And you can see as I go through and I look, each one of these little circles is basically a processing task, and it's going on and on and on, but it's basically doing this seamlessly behind the scenes. And okay, what I think I forgot to do is, and I forgot to do this, so let's say if I compute it, and knowing my luck, it's not going to run. It's probably going to crash because I forgot to go ahead and follow through with the computation. But right, it's com compute. It's going to take a little bit, and so that was the. I'd have to go back up, but as I recall, it was the subsetted means of like all of the different subarrays, chunks. So here I've actually generated it, and if I'm not mistaken, I can go ahead and also rerun the type to see what it actually produces. There's more efficient ways to do it than this, but this is on the cuff. And so it's actually returning an ND array. And so Dask does not actually do the computations until you tell it to actually compute them or run them. Okay, so the next little thing that I was going to go over is working with catalogs. Very few people are working with catalogs with intake yet, but it's some of the work that came out of Anaconda IO's work on just dealing with the morass of data sets. And so intake's philosophy is to contain a clear separation of the concerns between the provider of data and the consumer of data. So someone who cares about where a particular data set is stored and it's in the right format, etc., for best retrieval, they actually create these catalogs. And so once you give them to the user, they can just use it and they don't have to worry about where the data set is, etc. Well, as long as they actually have access to it. But I'll actually show you as I'm going along how you can basically use some of these things. Now, as a note, intake and also uses the Amazon S3 cloud, and the S3 FS computing. And did I? Okay, if you went all the way back up to the top, there was a comment I made about intake and S3FS, is that there was a recent change a couple of months ago, and it broke a bunch of backwards compatibility. And so I left a couple of instructions on how to download specific versions of intake and S3FS in order to make this example work. I think that was the only one that actually broke this way. And so hopefully I actually have enough information for you to go home and to install everything, whether it's an Anaconda or raw in your system, and to get it all working. And so I go ahead and load that in a plotting package. And I want to go ahead and open the output notebook, which is enabled plot source API, so that we can actually look at some stuff later on. So the intake data sets are loaded by data drivers, which are class definitions, some of which are included in the main intake package itself, but many of which are available as extra installs, and you can go to the plugins directory. Sorry, I didn't make that a hyperlink, but that's all part of the intake documentation. The currently installed set of drivers are listed by name in the registry. There's the YAML filecat, filescat, aliases, CSV, etc. And each of these are associated with an intake open function. And the registry, between the registry and these functions, are built and at import time by scaling all the installed packages with names starting with intake, and contain data source subclasses at the top level. It is also possible to refer to the drivers by fully qualified names, but this example will concentrate on the CSV driver, which is included in the default install. Commonly, the first step to writing the catalog entry might be to use the relevant open function to create a data source, and I will be doing this down below. And so, so I go ahead and use intake. I'll open a CSV file. Again, it's CICE from CICE data set. I think I also used it up in Pandas above. And so by doing this, I just created a data source. So this is an intake data source. And which has been verified by the arguments. Everything is working okay, but it did not actually access the data, i.e. this is a lazy process, just like Dask. So it sets some stuff up, but it doesn't actually read everything in until you tell it to read. So it only reads what it needs to read. And so if you remember back when I had a process where I created a data set and then I subsetted it, et cetera, et cetera. If I'm not mistaken, Dask is actually smart enough to actually prune some of the graph so it doesn't actually bother to do all the execution. And I was able to do this because I waited until I ran the compute. Now, don't quote me on that, but as I recall, that is the case. But regardless, with intake, what you have is you might have, a 5 petabyte, data collection, and I might turn around and say, I want to access just a small portion of it. And so it will actually only read it when I tell it to read it. And so here I tell it to discover. And so up until this point, it still hasn't actually read the data set. It's only told me what basically the data type, the shape, the number of partitions, and any metadata associated with it. And so as you see, I have time, I have the Arctic and the Antarctic columns, as you've seen before in the Pandas. And so this looks very much the same as it was above. And as you can tell, it's actually the source, or the discover actually returns a Python dictionary. And so here I can actually read it. So when I read it, I return a data frame, and I use head to actually print out the first 5 elements of the data frame to see, kind of, does the data look safe and sane? And as I said before, I'll often sprinkle these things in, which I can take out later or comment later as I'm developing code, to just get a good idea that it really is working the way I think it's working. So, we find that the data loaded fine, etc. And having gotten there, we might attempt to investigate some plots, which shows best the characteristics of the data. So here I'm going to use hvplot, which I haven't shown you before. And you can see from the data frame and the single line, not only does it show this very robust graph, but you'll notice that, whoops, I also have some functions over here where I can move the data, I can zoom into the data. I can also do things like, hover over the data, and it actually tells me which variable it is or which column it's from, the time, and the actual value. In places where it overlaps, it actually gives me both of them at that point. You can zoom out, can save this. There's lots of really cool things that you can do with this. And so this is a very, very useful data exploratory tool. But it does not really print, publication quality graphics. We still have to go back and work with it later. So now, one of the things that when you run this at home, you'll notice that it takes a while to actually process. It's actually going through and doing a whole bunch of stuff. But the identical output can be had from the data source instance too. So you'll notice that I did the data frame above, but here if I use the data source, it ends up actually executing much faster. And this loads the data directly every time, which may or may not be desired. It is possible but not included in this tutorial, to also specify data sets, a data set with cache on first access, so that the overall process is sped up greatly and improved. And so there's a lot of really cool features that, I haven't shown here. And so I'm going to go ahead and you can output the YAML representation of my data source. And you can see that I have the exact same URL path that I passed in before, and it tells me what driver it's using. And finally, I can create a YAML syntax catalog from containing or file containing that precipitation data with some extra descriptions and the addition of the plot that we just did above. And so I'll go ahead and add the CI, URL path. I'm going to give a description. I'm going to say I want some stuff about the plots, etc. And I'm going to load that. Wait, did I save it? Oh yeah, here. So, right, so I wrote the file c.yaml, and then, so I just created it here in the Pandas to create an external file. And then I'm going to go ahead and open that as a catalog. And so once I open that as a catalog, I can then go ahead and the plotting is automatic. And so here you see basically the same thing that I had before, but now it's doing it through the catalog, not through all of the stuff that I did before. Okay, so the catalog is functional and it's ready to be shared. The easiest way to share the intake catalog is simply to put it in a location where it can be read by anyone. If I actually would have had a more rigorous example for this, where I had, let's say, like all of the L2, all of the L1 data from the GEOS project, I could actually have a catalog that just covered that. And so instead of having to know where everything is, you could actually just go ahead and open the catalog, and here is an example, the same CICE example, but from the guy that originally developed that, this original tutorial. And I can just read that in and then take a look at the head here. And if I go back above, I'd see that it should be, I think, the same data as before. And so this is actually reading it in externally. And so, and then again, I can print this back out and take a look at it, and it looks exactly like I had before. Okay, so the last, first off, excuse for the typos and stuff like that. I once had 10 points taken off of my geometry homework for spelling, and I don't have the spell checker, automatic spell checker thing installed in my Python notebooks yet, so or Jupyter notebooks. So my apologies for some of that. I'll try to clean that up and make it available later. But anyway, so since this is a symposium on machine learning and genetic algorithms, I took a look at what all algorithms and things that people have been working with, and I decided that there's one or two people had done something on random forests, and those kind of classifiers. I've also seen a couple of other things, but I didn't see anybody working with genetic algorithms. And so I wanted to go ahead and present, and this is one of the canned examples from a group called DEEP, which is the Distributed Evolutionary Algorithms in Python. It's a framework for rapid prototyping and testing, basically, of ideas. but it works hand in hand with multiprocessing and other things. For those of you that don't know, and I do apologize for not having a better example of this, but I mean, pretty pictures explaining about genetic algorithms. But basically what genetic algorithms does is it uses an analogy to our DNA, where every gene is a variable and it has a position or a name. And so when you have individuals, you have basically the same named genes or positional genes in both individuals. And when you have the mating, the recombinant DNA, there's portions you get from each of your parents, and there's a small possibility that you'll get a little bit of mutation. And so that creates the individuals for basically the children of the next generation, and then those are run, and then those are paired up, etc., and it goes on and on and on. And the little mutation basically helps you to actually explore outside of the search space that your initial population was set up with. And so I've actually used this to really good effect with setting up a calibration for the hydrological model CREST. And CREST actually uses I can't remember, I think it was which of the optimization techniques internally, but it doesn't actually cache its work as it's going along, and it also doesn't allow you to run as multiprocessors. So when the hydrologist professor and his staff that actually developed CREST initially, it took them 6 months to basically run through the calibration for their first large basin model in, I think it was in Egypt. And the thing is that we've got supercomputers, we've got other techniques, etc. What Dask and Scoop allowed me to do was to turn off their internal calibration model or optimization model and use one externally, where I used very similar or the same tools and techniques, but Dask and Scoop allowed me to run them on the supercomputer. And it turns out that when you start playing around with this stuff, you'll find that you don't always want to have a population of millions of individuals, and because it just takes too long to actually find the best. And if you have it too small, it too quickly basically fixates on, I'm drawing a blank on the technical term for genetic bottlenecks. Yes, it'll very quickly bottleneck. And so you play around a little bit to find the size of a good population that doesn't converge too quickly, but it will converge in a reasonable number of generations. And with a population size of 60, I was able to run all of the models or all of the different calibrations, and then allow Deep and Scoop to actually calibrate the model. And over the course of, I think it was about 100 or so generations, it ended up eating about between 5,000 to 10,000 hours of CPU time. But instead of waiting 6 months to have a single CPU on a single core process the stuff, I was able to do it in, I think it was a couple of days. Not only that, but I was able to actually cache the generations before it goes and it would actually run the evaluation function, which in my case was to run the test data through the entire model, which could take as much as 2 or 3 hours to run that test data through each model. And so if it crashed for some reason, I could basically reload it and only lose what I had lost, up to that point. In those evaluations, and not lose the entire calibration run, which was one of the limiting factors for the original code. So anyway, the best individual is called the Hall of Fame. As I mentioned, this is very good at parallelism. There's multi-objective functions with SPEA, MO, CMAES, NSGA, both 2 and 3. There's other evolution strategies. It's actually it's extremely useful. And they actually have examples for alternative algorithms such as particle swarm, differential evolution, and estimation of distribution algorithms. Let me see. So the example that I pulled out of their code explicitly looks at the n-queens puzzle. I've given a link to the source. I was going to also write up what n-queens is about, but if I remember is how many queens can you put on a chessboard, and they don't basically cross each other so that they can't take each other. And so if I give here, I'm giving an initial size of 5. I forget what all of these weights and items, etc. is. Now, one thing that's interesting is that by default, Dask and Scoop actually runs a random seed each time, but you can pass in generate a seed offline and feed it in so that it will behave the same every single time. So this helps with debugging and for demonstrations, but also if you find a seed where it triggers a bug, you can actually cache that and go back and actually, debug these things, which can be mind-bending when you think about how this is distributed across, maybe, 100 or 1,000 cores. And so I'm going to attach a fitness function where I'm going to have a set function. So you can attach, different things, including, the population, how you actually initialize individuals. I want to be able to generate random ranges, etc. This is part of the, wait, did I remove the wrong? Ooh, I hope I didn't do that. I hope this is the n-queens problem and not the knapsack problem. If so, I may have removed the wrong one. Or left too much stuff in there where I was looking at different things. But anyway, going back up, this is how I evaluate each individual. I look to see if the maximum, if the individual has more than the maximum items or the weight is too much. This is the crossover, so I decide how I'm going to actually basically take the two individuals and then modify them and return them. And so I actually do an in-place here. I actually do an in-place replace between the two pieces. And then I also have a mutation operator that says less than half of 1% of the time, I'm going to grab, if the length of the individuals is more than 0, then I'm going to basically I think I'm going to swap between the individuals. Yeah, take the tuple of the individuals, and I'm going to randomly basically choose it. So then I have in evaluation the mate, the mutate, etc., where I'm setting it up above. And here I'm saying I'm going to go up to 50 generations. I set my mu, my lambda, my mutation indices, if I recall correctly, and I can basically pass all those in. And I'll go ahead and also register average standard deviation minimum and maximum, so that on each individual I can generate some some data. And so I'm going to go ahead and run this through the algorithm. I'm going to go ahead and use verbose output so I can actually watch what it's doing as it's doing it. And then I'll return the population, the stats, and the Hall of Fame. And as I mentioned, the Hall of Fame is the best individual. And so it goes through and I'm looking at the minimum and the maximums of these, et cetera, et cetera. So basic statistics, it's going through and it runs through 50 generations. And the best individual is basically put up at the top. And and it looks like it can set 12 queens on the board. And so this is just a very trivial example of how Deep and Scoop works for genetic algorithms. They also do genetic programming for those of you into that. And as I said, this is just a trivial little example to just show you a new tool for your toolbox. And I hope you find it useful. So down below, I've got lots and lots of references that I put in so that you can learn about Pandas and X-ray and Dask and Intake. There's a few courses that I linked to. Now the Python Bootcamp is NASA Goddard has done boot camps for I think a decade plus, and over time sometimes they've had like groups of people teach them, sometimes they've had them professionally taught by Anaconda staff, sometimes they've had them taught by part of the Advanced Software Technology group that I worked for I think it was like a year or so, and they kind of bounce around, so I only provided one of those. But if you look at NASA GFSC's Python Bootcamp, you'll probably show up about 5 or 10 of them, and some of them will actually have like all of the Python notebooks to teach the course. And both the Advanced Software Technology group and the Python Bootcamp, they actually start pretty much with beginner Python, that they don't assume that you know pretty much anything, but very quickly they teach you the nuts and bolts to kind of get started and keep you going. And when I took the Python Bootcamp, I think it was in 2013, if I'm not mistaken, at Goddard. I was just learning Python then. And even though I program in like 30 or 40 different languages, the material in the boot camp was heavy enough that I could start with knowing very little about Python, maybe 100 hours worth of experience, and they kept me busy flat running for 10 plus hours. I forget, it was like 8 hours of coursework and a couple of hours of homework for the 3 days that they taught it. So so the boot camps and ASGT's Python courses and stuff are amazing resources. And ASGT had just did a series on using like Numba, which is a just-in-time Python compiler in both CPUs and GPUs with Dask and just visualization and stuff, and then of course all the way back down to Python 101. Let's just pick it up. What is it? Let's do our first hello world, etc. I've also added links to the genetic algorithm stuff that I did before. So, if you're ever curious about genetic algorithms or genetic programming, or looking at some of the tools for how other tools besides, Dask and Pandas and xray, etc., but other tools for distributed processing as well. These are really, really nice tools. So I probably am missing a few acknowledgments, but I definitely wanted to give a shout out to Jules at NASA's Advanced Software Technology Group for their Python courses, as well as Hernan Royas, who did a bunch of the Pandas stuff that both I and Jules had actually based this and some of the Python courses. And I think with that, I think I'm done with 10 minutes to spare. And I'll open it up for questions.
Thanks, John, for giving overview from Pandas, DAS, and then genetic algorithm. I think if you have any questions, we can take and discuss. Any last moment questions? We have 10 minutes. Okay. Okay. I think it looks like it was more informative and lot of stuff is there. And you have already given Jupyter Notebook. So and references are there. So I'm sure everybody will follow those, run the Jupyter Notebook and check themselves. Uh, that was really nice. Even I learned something new about Python. You are muted, John. We can't hear you.
Thanks. Yeah, I always try to mute when I'm not intending to talk. Okay, so I'm going to go ahead and write my primary work emails here. So if people want to get a hold of me, they're in the chat box. Yeah, if you have questions or whatnot, my given name is John Lee David. I go by the nickname Ebo. And so you can get me at john.l.david@nasa.gov and at noaa.gov. And so if you have questions, I'll do my best to answer them. Yep.
Okay, great. Thank you very much for John giving such excellent tutorial. Lot of things to take from here. Okay,
You are
then
most
I
welcome.
think that's it.
And
So
I look.
thank you. Yeah, sorry.
Oh, I was just going to say thank you very much for inviting me. And also, I look forward to trying to put something together about actual research that I'm doing in this stuff. So for next year. Well,
Okay.
thanks again.
Yeah, thank you, John. And thank you, everybody. See you tomorrow.
Thank you.
Yeah. Okay, Sharon. So I think that's it, right?
That is.
Yeah.
Are you a part of our
So
meeting at 4 o'clock? I don't know if
I
you are.
don't know.
If you're
Oh,
not in the
4.
email. No worries. Go to sleep. You get
Yeah,
to do that.
I was wondering that 4. Okay, 4 means after 1 hour, right?
Well, you have a good night.
Yeah.
Oops.
Yeah.
And we'll talk to you tomorrow.
Yeah. See you tomorrow
Okay.
then.
Bye,
Thank you, Sharon,
Ankush.
for
Okay.
assisting. Yeah. Bye bye.